my name is Tarkayan. My ID number is 18653.
My name is Jayakumaresh Jayabalan and my ID number is 16085.
My name is Fauziah Abdillah. My ID is 17778.
Assalamualaikum and hi, my name is Marsha Daeyana binti Shahrom, ID number 16587.
Assalamualaikum and hi, my name is Ridhwan bin Saleh, ID number 16586.
We are going to present about batch distillation. And there are two types of distillation available, which are batch distillation and continuous distillation. And what is batch distillation? Batch distillation is the fractionation of a multi-component mixtures into its pure constituents in atmospheric pressure in a single column at a batch operation. And it is widely used in industry, especially fine chemicals and pharmaceutical industries. And there are a few advantages and disadvantages of batch pack distillation. The advantages of the batch pack distillation is that it is flexible and convenient, as it allows us to deal with unknowns in the feed stream or the product specification, and it requires low capital cost. But the drawbacks are the high energy demand requires, and due to the high temperature, decomposition will occur in the feed stream. The schematic diagram of the batch pack distillation. The vapor mixture will rises from the evaporator and passes over the column, and it fully condenses at the condenser. The condensate from the condensation will run down the column, counter current through the vapor, through the packings and back to the evaporator. And the rising vapor tries to achieve equilibrium with the liquid among the packings. And in the ideal case, the rising vapor should be in equilibrium with the liquid, but in the actual case, there will be no complete exchange in between the liquid and the rising vapor. And now let us look at the efficiency of the batch pack distillation. We can evaluate the efficiency of the batch pack distillation by using the HETP. HETP stands for the height of equivalent theoretical plates, and it is defined by height of packing divided by the number of theoretical stages, and it is dependent upon the packing type and size, the gas flow rate, and the chemicals being used. And the higher the HETP, the lower the efficiency. So we want the higher the efficiency, so we will desire a lower HETP. And if the gas flow rate is low, the HETP will generally be higher because the packing is not completely wet.
Okay.
So now let us look at the efficiency of the batch pack distillation. The efficiency of the batch pack distillation can be evaluated by using the HETP. HETP stands for height of equivalent theoretical plates, and it is defined by height of packing divided by the number of theoretical stages. And it is dependent upon the packing type and size, the gas flow rate, and the chemicals being separated. The higher the HETP, the lower the efficiency. And if the gas flow rate is low, the HETP will generally be higher because the packing is not completely wet.
So now we'll explain about methodology. But first, we need to prepare refractive index and versus composition graph first. And for this one, we need to prepare a set of water ethanol mixture within a specific range. So for this one, we need to have 13 different concentration of water ethanol mixture, and we will measure 13 refractive index. So for that part, we will have a graph based on the data. So we move on to the first experiment, that is experiment A. The purpose of the experiment is to determine the height HETP for total reflux. So first we need to perform general startup procedures. Okay, after we reach the steady state value, we can record the temperature for the distillate and also the bottom product. And also we can collect the sample of distillate and bottom product, so that we can measure the refractive index for both for both part that we collected. Okay, so for the first one, we use heater power of 100%. So right now we can change the heater power to other value, and we can wait for 15 minutes first to allow the distillation unit to achieve stable condition. And then we can repeat like the first part that we use in the experiment. We can collect the sample for both sides, the distillate and also the bottom products, and we can measure the refractive index. After we collect the sample for both parts, we can calculate the theoretical number of plates, that is HETP, using McHale method. So we can also can measure the amount of ethanol left in the evaporator that's calculated and plotted against time using the Rayleigh equation. So now we can move on to the second experiment, that is calculate the HTP for constant reflux. First, like the first experiment also, we have to perform the general startup procedure, and after that we can collect the initial volume and composition of ethanol water mixture in the reboiler. So the heater power for this experiment is set to be 70%, and we stick until the end of the experiment. And after the steady state is reached, we can take the temperature for top and bottom products, and also we can collect the sample distillate and also the bottom product, because we can measure the refractive index by this data. Reflux divider was set to have a reflux ratio of 1, and we need to wait for approximately 7 minutes before we can repeat the sample collecting to measure the refractive index. So this experiment was conducted for almost 1 hour. So approximately we can have seven readings. So lastly, we can also calculate the volume of liquid left in the reboiler, and volume of distillate also can be collected and be measured.
As for results, there are 3 parts that we need to calculate. The first one is a sampling, and part A is batch distillation at total reflux, and part B is batch distillation at constant reflux. I will cover on the sampling and the part A. For sampling, we need to prepare the graph of refractive index versus the composition plot. So we already have the refractive index of all the samples. What we need to calculate is the composition of the ethanol. So how are we going to calculate the composition of ethanol? We are using the formula from the appendix A1. From appendix A1, we obtain the specific gravity and the molecular weight of ethanol and water. So we are going to use this information to calculate the molar volume of ethanol and the molar volume of water. So this formula is by using the specific gravity that we have, divide by the molecular weight of, let's say we have ethanol, we are using the specific gravity of the ethanol, divide by the molecular weight of ethanol. But since the specific gravity of ethanol and water is per milliliter, we're going to times with 1000 ml to have the conversion to 1 liter. So from that, we already obtained the molar volume of ethanol and water. Now, to have the mole of ethanol and the mole of water in that specific sample, we need to calculate how much are they ethanol and water in that sample. Let's say we are taking the first sample, which is the volume of ethanol of 0 milliliter and volume of water as 10 milliliter in the solution. So we use that volume, we use the formula of number of moles equal to molarity times the volume times the molar volume. So 17.1 g times with 0 liter from the volume of ethanol, we obtain 0 mole of ethanol in that solution. For calculation of mole of water, we use the molar volume of water, 55.9 mole per liter, and times with 0.001 liter. 0.01 liter, sorry, and that we obtain 0.5549 mole of water in that solution. So this is repeated for all the 13 samples, and then we can calculate the mole fraction of ethanol by dividing the mole of ethanol from this part and then calculate with the total mole. We add up the mole of ethanol and the mole of water. So from that, we can obtain the mole fraction of ethanol and the mole fraction of water. All these results are obtained, tabulated in this table. So we can see here is the volume of water, mole of ethanol, mole of water, mole fraction of ethanol, and the mole fraction of water calculated, and the refractive index that we obtained from the spectrophotometer. From the table before, we plot the graph of refractive index against the mole fraction of ethanol. So from this graph, we know the equation of the line that we have plotted, that is y equal to 0.1537x plus 1.3338. Since the y-axis is refractive index and the x-axis is the mole fraction of ethanol, we can now obtain all mole fraction of ethanol regardless of the refractive index that we obtained from the sample. So this graph is very useful for the calculation of part A. For part A, the batch distillation at total reflux, we make use of the equation that I have just said just now, which is y equal to 0.1537 plus 1.338. So we can calculate x from that. To recap that, x is the mole fraction of ethanol. So let's say we are taking refractive index of 1.3763, we substitute it as y in the equation above, so we can obtain the mole fraction of distillate and mole fraction of bottom. Now, for the last part of part A is to calculate the HETP, which is stand for height equivalent theoretical plate. So let's say when the heater power is 100%, we can obtain that number of theoretical plates is equal to 1. We given the height of column is 1120 millimeter, so we use the formula of HETP equal to effective column height divided by number of theoretical plates. It's equal to 1120 divided by 1. So yeah, that is the height equivalent theoretical plates for the heater power of 100%, which is 1120 millimeter. So that is repeated for the other heater power, which is 80%, 60%, 40%, and 20%. So this is what we get. This is what we get from the calculation before, the number of theoretical plates and the HETP. Actually, this is the graph that we use. To calculate the number of theoretical plates for that particular heater power. We plot the distillate mole fraction and the bottom mole fraction that we obtained from the calculation, and then we see how many plates can be obtained from between these two lines. So basically, for all the heater power, 100% to 20%, we obtain all one plate for all. So yeah, this is what the result of the HETP versus the heater power. Thank you.
I will discuss the result of experimental A, which is batch liquid reactor. From the result, we have determined the heat equivalent theoretical plate, and we will study the effect on liquid and vapor loading on each ETP at total reflux. Let's take a look to this graph of refractive index against mole fraction of ethanol. From this graph, we know that when the reactive index increases, the mole fraction of ethanol also increases. This is due to the density of the mixture. Since the mole fractions of ethanol increase, the density of the mixture will be decreased. Then the refractive index is increased. This is because the refractive index is inversely proportional to that density of the mixtures. So what is RI, or refractive index? Refractive index is the properties of the liquid. So what is reactive index? Reactive index is the physical properties of the liquid. So why we don't use another physical property such as maybe density or viscosity? This is because reactive index is easily to be calculated with high degree accuracy, and the most important thing is less time consuming. Next, from this table, as the heating power increase, the product of distillate is increased, but the bottom product is decreased. Regardless of this increase in the heating power, the distillate product will higher in the value of that in the bottom product. Why is it like that? Because more volatile product will concentrate in the top of the column rather than in the bottom of the column. because the more volatile product concentrated at the top of the column. That's why we have the distillate product higher than that of in the bottom product. Theoretically, the higher the heating power, the purer is the product. We can compare the refractive index of the pure ethanol, which is 1.309, to the 100% of the heating power. The value is closer to that 40% of the refractive index, which is 1.3608. Why is it like that? Because this is due to some error that occurred in the experiment that I will explain later. From the graph, we found out that theoretical plate for all the heating power is the same, which is 1. Theoretically, the higher the heating power, the more is the theoretical plate. This is due to the limitation of temperature, which I will discuss later. From this graph, the value of HETP is constant when the heating power is increased. Theoretically, the higher the heating power, the smaller is the HETP. Again, this is due to the limitation of temperature, which we can see in this table. The temperature is only small change in temperature. We can consider if the temperature is constant. If we see from this table, there is only small change in the temperature because the system will remove the excess heat in the system. That's why we will have the almost constant temperature. From the experiment A, we know that the higher the heating power, the more is the theoretical plate, and the smaller is the HETP. The smaller the HETP indicates that the small column and the more efficiency is the column. But from the experiment, we know that there is some error, which is human error and the stability of the system. The human error is because we are not directly close the file, so there are excessive evaporation of the ethanol, and the stability of the column will that cause the heat axis will be removed in the system, so that we will have the constant in temperature. Thank you.
Now I am going to talk about the results and discussion of experiment B, which is the batch distillation at constant flux. The objectives of experiment B is to study the changes of top and bottom composition sample over time in batch distillation at constant flux. The second objective of this experiment is to determine the height equivalent theoretical plates, HETP. This table shows us the data that we had obtained from our experimental result. As you can see, there are two types of product, which is the distillate product and also the bottom product. Each reading that we take consists of 7 minutes. So we have taken 8 readings, which consists of a total of 49 minutes. From the table, it can be seen that the top product becomes richer in ethanol, while the bottom product is lesser in ethanol. This is due to the lower boiling point of ethanol, which is 78.3 degrees Celsius, while the water is 100 degrees Celsius. Therefore, at each time interval, the mole fraction of ethanol is higher in the distillate product rather than in the bottom product. Moving on, the number of theoretical plates is calculated using the Machiavellian method. One assumption is made that there must be an equal mole of overflow through the tower between the feed inlet and the top tray, and also between the feed inlet and the bottom tray. From the experiment result, it is shown that the number of theoretical plates is constant at 1 from 0 to 35 minutes, and it increases to 2 from 42 to 49 minutes. This obeys the theory that the number of theoretical plates should be increased with time. As you can see, this is the graph of HETP against time. From the graph, we can see that the HETP decreases when the time passes by. Theoretically, HETP is inversely proportional to the number of theoretical plates. The higher the number of theoretical plates results in the lower value of HETP. And this is the graph of amount of ethanol left in the evaporator against time. From the graph, as time passes by, you can see that the amount of ethanol left in the evaporator decreases. The final volume of ethanol is lesser compared to the initial volume of ethanol left in the evaporator. And this is true since the ethanol is used during the experiment as the time passes by. That's all from me. Thank you.
Alright, so right now I would like to explain about the conclusion for our experiment. So for the first experiment, first part of the experiment, we can see that the number of theoretical plates was kept constant when the heater power is decreases, and we can also see the mole fraction of distillate was decreases when the heater power is decreased. And lastly, the mole fraction of bottom products is opposite compared to the distillate. It increased and suddenly become constant when the heater power is decreased. So let's move on to our second experiment, that is for constant reflux. We can see that there are a fluctuation occur in the flow rate when the time increases, and we can see also the mole fraction of ethanol at the bottom products is decreases when the time increase. This is also because of the decreases of bottom products when the concentration of ethanol is decreases. And the last one is the number of theoretical plates was kept constant at first, but it suddenly become increases and cause the HETP value to be decreases. Since the HETP value is decreases, it shows that the efficiency of the separation process is increases with time. With that, the efficiency of the batch distillation pack unit will increase with time. So that's all for our experiment. There is batch pack distillation. So thank you.